Good morning. My name is Hardev Singh. I lead the AI product strategy at Arista. I also work very closely with our cloud titan, accounts. And today, in my session, I'll be covering, the AI landscape in general. I'll go into the different networking product solutions we have for AI, and then also touch on some of the challenges we're seeing in terms of power and some of the new optics technologies and different solutions we have. So when we talk about AI, we talk about networking. There are two aspects, right? You have networking for AI. My session today is going to be focused on networking for AI. There is a lot we do, which is AI for networking, right? There is a lot of features, a lot of solutions. We work internally to make our EOS, our solutions better, whether it's AI ops, a lot of stuff on observability. There are AVA sensors that are on our switches, security, features like SSU, which is smart switch upgrade for an AI network that's critical. You have this critical network running, and you want to upgrade, or you have a security patch. You want to do that, pretty seamlessly, and predictive analysis. So, what is our company's strategy in terms of our products and software and manageability? Now, any product we have at Arista, whether it's a campus switch or a WAN router or a data center, large 400 gig, massive 576 port switch, any product runs that one single binary EOS, right? And there is one single management software, which is CloudVision, right? Which gives customers that flexibility, that end-to-end kind of solution to run that same high quality software, no matter what solution, what product running at Arista, right? And that's what customers kind of really appreciate and like. So if you kind of look back, the networks have always been in these silos, right? So we have the traditional data center front end network, and then we've had kind of what we call the backend network, and historically that's been HPC, right, and which is dominated by InfiniBand. Now what we're seeing in AI is what we call it as the AI center, right? Not the data center, the AI center, where we have now the backend network, which is basically the network connecting to the GPUs, right? And then the front-end network, which is connecting to your traditional data center network, connecting to the storage, to the WAN, basically all different aspects of a network to give you that one AI center.
Hardev, you mentioned on the prior slide, consistent network operating system, understand that, consistent operation through your cloud service. But you also mentioned consistent state management. And how does that play out across multiple levels of switches and all this other stuff?
Yes, very good question. So that state, or the NetDB state that we have in our EOS operating system is really valuable. Especially, I'll give you an example in terms of AI, where visibility is key, right? That state can be now pulled into, could be CloudVision, could be any other kind of telemetry software where you want to see what's going on within your network, right? Especially in an AI network where, if a link goes down, or you're having, link flaps, you really want to make sure that, those links come back up reliably and you're able to troubleshoot it quickly, because you've got these expensive GPUs working on these workloads. So that state streaming really helps kind of into the visibility aspects, right? Good question. I like to kind of show this slide. This is from the 650 group, and it shows you how the data center ports or speeds are historically been, and then how they're kind of forecasted in the coming years. And what you see is there is an explosion in the high-speed ports, and they've kind of clubbed the 800 gig and 1.6T together, which kind of makes sense. 800 gig is based off 8 by 100 gig SerDes, and then 1600 or 1.6T will have 100 gig SerDes variant, 16 by 100 or 8 by 200 gig SerDes. But all of that increase, and if you look at the ports, is almost 30-40% of the entire network is attributed to AI. The explosion in AI networks, the XPU clusters that are being built today, a lot of it is for training, and then we believe in the future inferencing or serving that data that's been trained is going to be another big factor pushing that. And then basically the I/O needs to keep up with the XPUs, with the GPUs, right? And then if you look at the slide on the right, you see the 51.2T ASIC, which is basically the 800 gig chip, has pretty much, if I want to say, the fastest ramp in the history of chipsets. You just see an explosion. So in my mind, this is probably the fastest transition of speed from 25.6T to 51.2T. And I would bet the 100T will kind of transition equally faster. So traditionally, the speeds have taken many years to go to the next one, but with AI, you just see that transition happening every 1.5 to 2 years, to meet that bandwidth from the XPUs or the GPUs. So let's talk about our Etherlink AI portfolio.
Hardev, what do you think is driving that increase in bandwidth to be so quick compared to what it's been in the past?
AI.
Thank you. Yeah.
Andy.
XPUs. It's the GPU, or what we call XPU accelerators. Their performance is at a much faster clip, and then the network is kind of trying to keep up with that bandwidth. So
I understand it to a large extent for the backend network, but vast majority of the ports out there are not GPU to GPU port configurations or switches. I mean, you're showing a vast increase in the highest, 52 point whatever terabit per second. This is a chip, right? I mean, this is a switch chip.
Correct. So yes, that explosion is attributed to AI, but having said that, your front end and your backbone also needs to keep up in some extent. So that 400 gig and 800 gig will also kind of get deployed in the backbone. Even the storage is kind of moving to 400 gig. So it's a combination of many things in the network, but largely attributed to the GPU connectivity for that high speed. Yeah. So coming back to our hardware portfolio, this was announced at our June 10-year anniversary event in NYSE. Basically, we have a full suite of 800 gig products. So on the left, you see we have fixed and modular systems. The fixed box is based on the 51.2T Broadcom silicon. It gives you 64 ports of 800 gig. Today, the XPUs, the NIC connectivity is at 400 gig. So it's really a 128 port 400 gig box, right? Pretty good radix. And then if you look at our modular systems, and in some sense, this is our flagship AI spines with the largest chassis, you can actually go up to 576 ports of 800 gig. So if you have a customer building a smaller size network, you could just connect it to one big chassis, right? That's 1100 odd 400 gig ports. That's almost half petabyte of bandwidth out of one chassis, right? And then if you look at a leaf spine network, if you're building large clusters, we know today some customers are building pretty large clusters that can go as large as 100K GPUs, even higher. Then the most optimal kind of design is a leaf spine design for the back end, where within a 2-tier network, leaf and spine, you can get build a cluster that as large as 70, 80,000 GPUs going to hundreds of thousands of GPUs. Now, why it's important to stay in that 2-tier is because the number 1, 2, 3 problem in AI is really load balancing. You want to have well-hashed load balanced traffic so that you're not starving any link, there's no congestion, because that one GPU can hold up the job for all the other GPUs, and you've got to keep going back to checkpoints, which can be disruptive and, more importantly, expensive, because there's a high power hungry network. And then the latest product line. Yeah, question. Yes.
Bandwidth is great, but I mean, it's also latency. It's being able to get the frames across and stuff like that. So okay with bandwidth for AI, but
Yes.
latency is a big part of the picture. If something is delayed for, I don't know, 100 microseconds or 100 milliseconds, this is a serious challenge in this network.
It is. You bring up a good point. And latency is important. And that's where designing and kind of operating your AI network plays in. Now, if you have a unique workload for AI workload, you can actually use different parallelism techniques, wherein the way you kind of design, for example, you can have AI pods and then kind of connect them with a super spine. And then if you have good localization and good parallelism, with tensor parallelism or the fully sharded version, you can play with the latency aspects and choose different parallelism techniques and localization so you kind of manage the latency. So yes, your broader comment is true, but you are able to fine tune your network as well as your AI workloads to kind of see what suits you better.
So the expectation is that whoever holds the equipment will do that, or you're actually helping out with this equipment?
So good question. It's a combination of network features that are available here, but it's really the AI teams or the AI network teams at the customer side who are building this to kind of really fine tune and figure out those right knobs that they want to tune. Yeah. And I was coming to our latest architecture, latest product line, which is the DES, the distributed Etherlink switch. This is a single hop interconnect. Even though it's a two-tier network, it's a single hop. What I mean is you have two switches, a leaf and a spine, but the main chip is on the leaf. So the lookup happens there, and the spine is just acting as a fast kind of switch through. So you have a single hop, and with that network you can build a pretty large cluster. And in the following session we're going to kind of go. Hugh's going to go deep into that architecture and
It looks
the
like
benefits.
almost InfiniBand, the back end.
Not really, but yes, if you're interested, we can go and explain the architecture and the benefits in detail. Yeah, and with that with that architecture, you can then scale to tens of thousands of nodes, right? Quickly, this is the 51.2T box. Like I said, 64 ports of 800 gig. This is based on the 5 nanometer node, so it's the lowest power. Again, I keep coming to load balancing, and the other most important problem to solve in an AI cluster or a network is power. So power is kind of becoming the number one top of mind issue for customers. And LPO, which is linear pluggable optics, is a direction that the industry is moving to kind of really help the power angle on the optics and also the network. So any amount of power you can save from the network side, you can use that and kind of power more GPUs or more XPUs.
Do you have some numbers about that? I mean, is it?
I do. I have some examples in the coming slides. This is a cool little innovation, hardware innovation. So the feedback we got from our large customers is like, hey, if something fails in a box, it's just a pain to kind of unplug all those cables in the front, take the box out, service it. If you look at a system, the components with kind of the lowest MTBF is usually your RAM, SSD, or the CPU. So what we did is, if you remove the two fans on the right, you can actually pull out the whole CPU cluster. Yeah. And there's another advantage. Some customers, when they're servicing it, they have proprietary data on the SSDs. They either have to kind of trash it or kind of be very careful with that. So with this being a fruable part, you could just kind of destroy it, or so it gives that benefit as well. So just a cool little addition on the hardware side. I spoke about our chassis. The 7800R4 is our latest generation with 800 gig line cards. So on the largest chassis, you can get up to 1152 400 gig ports. So like I said, it's almost half petabyte of data. And this is a fully cell-based VOQ architecture. So within the chassis, you have perfect load balancing, right? And it's kind of ideal for customers who are building small little clusters where a single chassis might suffice as a network, or when you're building large, massive clusters, this is a perfect AI spine, right? So you've seen.
I'm getting caught on some semantics here. Are these shipping products? Because next generation to me means that it's not here yet. Are these shipping products that I can order and get delivered this year?
They will be shipping this year. Yes, they are in customer trials, actively being tested. They will ship this year. Yeah. Yeah, the 7800, another point I was going to make is, Meta is public about their 24,000 GPU cluster, and they talk about the 7800 as their AI spine. The 7700, like I said, this is a new product line for us, the AI distributed Etherlink system. This is a single hop, and with this combination of leaf and spine systems, you can scale and have a cluster that's as large as 32K in a single hop. So like I say, it's a single lookup, a single hop, even though it's a two-tier network. And we're going to cover this in detail in the next section, right? But the same EOS, standard Ethernet connectivity, LPO support, pretty much the same feature set that we support on a 7060X6 as well as the 7800 modular chassis. There was a question around different, scale numbers and power, which I'll cover. So if you kind of compare the three different, product lines in a single tier, with the 7700, you can scale, from 4K to 32K. The 7800 chassis will give you up to 576. All the numbers here are keeping 800 gig as the reference. You can multiply by 2 to get the 400 gig number, and then 64 ports on the X6. And then once you go to two-tier, you can scale to pretty large numbers, which is a lot of bandwidth, right?
What's the difference between VOQ and RDMA-aware load balancing?
So VOQ is the architecture within the chassis where you have virtual output queues, wherein you have buffers where you're going to spray the packets between the ingress and out and the egress port, and it's fully scheduled. The RDMA-aware is basically load balancing. We call it dynamic load balancing, and we have some other load balancing features as well, which are more aware of the RDMA traffic, and you can based on that you can balance or hash.
So if you were designing a medium scale cluster, I guess these days, which would you prefer, the VOQ or the RDMA aware?
Both work equally fine, but when you mention a medium sized cluster, and I'll take an example, let's say it's under 8,000 GPUs, you could build perfectly with a two-tier 7060X6, right? And then once you get to a large tier, then you can use either a 7800, 7700, or one of the most common designs is to use a 7060X6 as a leaf and then a chassis as a spine, right? How am I doing on time? Okay. This is kind of giving you a picture of the entire kind of network, right? So you have the traditional front-end network, and then you build a separate back-end AI network. And then again, depending on the size of your cluster, you can have it with smaller fixed boxes or chassis or a mix of both, or you can even go three-tier if you really have building a very, very large cluster. But the key thing is here is you also need to look about storage. So for AI backend, you pretty much want a dedicated storage for the backend and then a dedicated storage for the front end. And then obviously you have WAN connectivity. This kind of gives you an overview of a large AI network. Yeah. We have great hardware, but the crown jewel at Arista is really our EOS and the feature set. And in AI, load balancing, like I said, is key. We have a lot of different features, DLB, CLB, hashing based on RDMA headers, and congestion control, right? So DCQCN, which is ECN, PFC. We have, again, enhanced features, PFC watchdog, and then multi-tenancy, right? If you're building a GPU cluster, XPU cluster, and you want to offer it as a service, you want segmentation. You want to be able to do multi-tenancy, and that's where VXLAN EVPN, comes in for Ethernet. And then once you've deployed all this, it's really monitoring and visibility. You want to have, all that telemetry data, to look at, where the congestion is, where the links are failing, and how can I quickly recover that and, have a reliable, robust network.
When you mention things like these, advanced, use the word advanced. Is this also consistent with like a commitment to like P4 or other things in that nature, or is this completely separate category?
Yeah, maybe the right word is more optimized.
Optimized.
Tuned.
Okay.
Yeah.
Okay. Very good.
Yeah.
Along these lines, are you members of the Ultra Ethernet Consortium? And
yes, we are. We are the founders of one of the founders of Ultra Ethernet Consortium, the early members, and we've been working very closely. My next presenter, Hugh Holbrook, he's our representative in the steering committee. So there, okay. we have some information on that.
Yes, if you just go back to that slide, I was wondering, a bunch of these things are addressed by various different features in Ultra Ethernet, and I was wondering, are you looking at Ultra Ethernet to handle, like, I would say, quite a few of these?
Yes, we are very closely working with UEC, but UEC really, the big benefits are going to come on the NIC side, right? Wherein there are capabilities of better congestion control. You're going to have packet spraying at the NIC level. Better, basically, enhanced transmode protocol. That's what really it is, right? So yes, short answer is yes. We're heavily kind of working with UEC, and if it's of interest to you, we can talk offline. We can give you a pretty detailed explanation. Yeah. Okay, let's move to the fun side, which is optics, which are becoming equally important in an AI network. So if you looked at the 400 gig optics, there's a mismatch between electrical and optical. Right? Your electrical is at 8 by 50 gig, and your optical is 4 by 100. At which point you need a gearbox, which does that 50 gig electrical to 100 gig optical conversion. The gearbox also helps you amplify the signal. What does that gearbox do? It adds power to that optic. It also adds cost, right? At the 800 gig speed, things are linear, which is great, right? Your electrical is 8 by 100 gig PAM4. Your optical is 8 by 100 gig PAM4, right? So you really have that SerDes speed matching with the optical speed, at which point you're going to get the lowest cost, less complex optics. And the remaining part of my presentation is going to talk about, the power and the different, different things we're looking at to kind of reduce that optical power. Within an AI cluster, if you were curious, what are the more popular optics used for connectivity? Most AI clusters, you have an end of row design, so you'll end up using like a 800 gig VSR4, which gives you 50-meter reach, is enough to reach any GPU from the end of the row on the rack. And then between the leaf and spine, you could use an XDR4 or FR4. One goes up to 500 meters, the other optic can go up to 2 kilometers, right? Okay, so let me kind of dive into the AI landscape. Yes, the LLM models, just keep increasing. The latest, ChatGPT is over 1 trillion parameters. But the I/O or the silicon is also doubling. And I was talking earlier how the speeds are kind of doubling every 2 years to kind of keep up with the Gen AI kind of, training clusters that are being built.
So your chart there is assuming linear growth forever. When will that stop happening?
It's a good question. We think it's going to continue that way for at least the foreseeable future, and where the
how far is your foreseeable future?
And by the way, that's log growth. That's not linear. The left scale's log.
No, but yes, there's a log scale, but it's still linear growth at some point.
Well, we're talking about Gen AI now. I'm hearing, AGI, so, if those kind of trainings kind of become valuable, then, we'd have to kind of keep doing that, and these technologies have to keep up, right?
So your assumption is that this will keep going until it doesn't?
Until it doesn't.
Okay.
That's a fair way.
We have no idea when this will stop.
I would say that.
Okay.
Yeah. So coming back to reliability, if you have a giant cluster, a large AI cluster, stuff's going to fail, right? You're going to have, HBM, ECC errors. GPU drivers are going to get stuck. Optics are going to fail. NICs are going to overheat. That's a common thing. That's an MTBF thing, and that really slows down your cluster. You got to keep going to the previous checkpoints. So Ethernet is proven to have high recovery, and kind of really brings those links back up. And with EOS and the visibility, you're able to really monitor that network and make sure those those expensive compute hardware you have are kind of doing the jobs, right? So a best of breed network, right, is critical for AI, and it kind of pays for itself over time. So the Ethernet ecosystem, right? We hear about the GPUs in the market, but the cloud service providers are also designing their own AI chips, right? Many of them are public about it, and we see a significant kind of growth there. A wave of startups are looking at XPUs, and the focus now, I believe, is really to try to solve the inferencing problem, right? The training is happening, but then you want to serve and inference, pretty quickly. If you look at the TSMC nodes, 5 nanometers in production, you have 3 nanometer and 2 nanometer. The point I'm making here is if you look at the density multiplied by the speed or the isometric area, you will double the bandwidth, or when you go to the 2 nanometer from the 5 nanometer, and keeping the power the same. What it really means is if you design the same chip with the 2 nanometer, you're going to get twice the performance, right? Keeping the power at the same level. So the projected, there's a question, what do you see as the projected XPU performance? We believe it's multiplicative, right? 2x process improvement going from 5 nanometer to 2 nanometer. Larger silicon substrates, the substrate technology with CoWoS, chips on wafer on substrate, and then architectural improvements. We believe there's at least going to be a 20x improvement, over the next 2 years till 2026. Right?
So in your prior chart, if I was to put just for an executive to explain, we're going to forklift everything we've invested in so far, where would the forklifts be on that graph to take out the old equipment that can't keep up?
That's a good question, and you would really do your math on amortizing the stuff you have, and then the power benefits. If I'm constrained on power and space, maybe it's going to be advantageous to go to the next node on the XPU as well as the network to get the maximum buck out of
That's more where I was going, is to understand, there are always constraints,
right?
And it's okay, we've removed some of these bottlenecks, so where are the constraints now? And you did mention before that power is
really the main problem.
Yeah, so that in order to choose where am I going to make my investments, what am I going to change, which component do I swap out that is going to give me the best benefit given those constraints, because I have different options about how that will do. But if I remove that bottleneck and I have an incredibly fast network now,
yes,
do I actually have the data to be able to drive that? So I've just moved the bottleneck somewhere else?
Absolutely, yeah. Other way to think about it is, and this is more outlooking into the future, within the chassis or the rack, copper is going to be your best friend. It's going to be the lowest power, lowest cost, and most highly reliable medium. Liquid cooling is helping racks kind of go from higher density to the next higher density. If you look at the NVL72 rack from NVIDIA, It has 72 GPUs, 120 kilowatts. We think the next generation probably double or quadruple that size, right? The number of XPUs you can put in a rack. And then from rack to rack connection, you need optics, right? And then if you have a large cluster, those optics add up pretty fast and the power adds up pretty fast, right? Here's an example of the NVL72 rack. If you look, there's a full mesh copper backplane, right? Letting them kind of get you to that 120 kilowatt on the rack. If you use that as an example and you use optics to connect those 72 GPUs, you'd be spending at least another 20 kilowatts just on the optics connectivity for that rack. Right? So let's shift to the SerDes. So today the SerDes is 112 gig SerDes on the 800 gig, and then on 1600 gig you're going to move to 224 gig SerDes. Again, this is probably the fastest in the history that the SerDes speeds have moved, so fast, 50 gig to 100 gig SerDes, and I think that will continue, right? So 800 gig is 8 by 100 today, and 1600 gig will be 8 by 200. So you still have that 8-lane, linear interface to kind of get you that lowest cost and power. Right.
Can I ask you a question
yes.
quickly? I heard you say, and I just wasn't sure it was correct. Did you really mean 120 kilowatts in a rack?
Yes, that NVL72 GPU rack is 120 kilowatts.
Okay.
So you can see how this is perfect for all the legacy data centers in Europe.
That is, in one rack. That is just how do you get that in a building?
And I was
talking about forklifts earlier.
I would argue that will go to maybe 200 or 500 kilowatts is not unimaginable in a few years to get that many accelerators in a rack. Right?
So with that type of power, even if you have liquid cooling, you still need to dissipate the heat somewhere. Where?
And then and that's a separate discussion and topic by itself, right?
Under the sea.
Heat exchangers, there's liquid cooling, within the system.
Power weight cooling.
You kind of immerse the whole
yes,
GPU.
And you still have to dissipate that heat somewhere.
It's got to go out. I mean, the amount of power you're pulling into buildings and the amount of cooling ponds you need to cool this is just phenomenal. And
but liquid cooling is definitely exponentially better in cooling than air cooling for GPUs, and that's why that NVL72 is liquid cooled, right?
I understand for density purposes, but at the end of the day, you still need to either dissipate that heat into the air or evaporate water to get rid of it. Or if you're really stupid, to use refrigerated air to get rid of it.
I want to say, folks with PhDs in thermal cooling and all are going to be, hot. They're going
to suddenly engineering is going to be cool again.
You're going to need a polar layer, is what you're going to need.
So when they reference the liquid cooling,
there won't be any polar
yes, but what you're doing right now is creating a problem that you don't necessarily have a solution for.
Yeah.
Oh,
okay.
I'm not nitpicking what your technology. It's just there comes a point where this heat doesn't just.
No, this is a fair point.
This is where the OCP track on just the optical transceivers, just the heat from the optical transceivers. That there's an actual group just focusing on that one.
Well, I mean, you're talking about 20 kilowatts for an optical transceiver. That's 20 hair dryers,
right?
Just going full blast all day long, just to move bits across a pipe.
Terabits.
Terabits.
Talking about not bits.
Okay, yes, it's a lot of bits, but anyway, I didn't.
You're the scariest presentation so far for this AI Tech Field Day. Thank you. Terrifying math.
Yeah. Okay, so, I mean, two separate considerations. One is the total power dissipation of the entire data center, which is an issue, and you dissipate it into the environment in some way, water, air, and through lots of different technology. The other one is just within a rack, how do I evacuate that heat density into? And there's a lot of compelling reasons. The compelling reason. Probably the most compelling reason to compress many things into a rack to get 120 kilowatt or larger racks is because it enables copper cables. And copper cables they only have limited reach, but copper cables are much more reliable, lower cost, and they use lower power. And so if I can pack a lot of things into a rack, I can use copper cables within rack, and that has compelling advantages.
And
and so like they're just they're two related, but different.
So like everything else, it's a trade-off of the reliability of copper and
the reach of copper.
Which means you have to get more density, which means you have more heat dissipation, which means you also have to pull more power in to that physical location in one form or another, and trade-off. And I mean, we can continue.
Okay,
you could have a data center of a fixed power size and like do it in different, nodes of high density or distributed.
We've derailed you enough.
So power got everyone excited, yes. But from the network side, we play into the network and we're building, these switches. So we are also looking into liquid cooling technologies, and that's stuff we explore and look into all the time. So 800 gig, quickly pivoting to 1600 gig, we have a big problem. It's power again, right? 800 gig, your data center optics around 12, 13 watts. The DSP-based optics on 1600 gig, at least our initial assumptions, they're going to be at 30 watts. Now you have something called as LRO, which is linear rated optics, basically DSP on one side, and then you have LPO, linear pluggable optics with no DSP. And our guess is that the LRO will be 20 watts and maybe the LPO can be as low as 10 watts, right? Again, not to scare you, but if you do a rough math, in 2026, if you build a 100K XPU cluster, assuming 12.8 TIO bandwidth per XPU, needs 8 1600 interfaces, you're looking at 3.2 million 1600 gig optics. And if you use that with optics with DSPs, that's 32 megawatts of power with LPO optics and 96 megawatts with DSP, right? So there's the power of the DSPs is just too high, right? So yeah.
Is that 30 megawatts for the optics alone?
Yes. If you go by that 30-watt assumption that I showed in the previous slide, times that many optics.
So do you have any
slide up again, please?
Yes. Is Arista planning to make small modular reactors to put small? I'm saying again, like, show me the forklifts here, and you're showing me the forklifts pretty strongly.
You need to partner with Westinghouse.
No, we're looking at what this can be in terms of power and what can we do. So my next few slides want to be within time is going to see what is the solution for that power. And linear pluggable optics is one way to reduce the power. They're low power, low latency. The cost comes down because you don't have a DSP in it, and it's reliable because you have less components. Right? So the status of LPO at 112 gig at 800 gig speed, the MSA spec is nearly complete. Right? It should be published in a few months at ECOC. Multi-vendor interop testing is actively going on. The ecosystem is broadening. Many vendors have joined the MSA, and then we expect vendors ramping volume in 2025. Now, fast forward a little bit, will LPO, how does LPO look at 224 gig? Well, you really need a clean electrical channel. Your link loss margin should be under 15 dB. It'll most likely require flyover cables, and then you need a high performance TIA and a linear driver to achieve that. This is a picture of, again, that NVL72 rack. You see you have the NVLink switch chips over there, and you have the connectors, and you have flyover cables connecting to the back plane, which then further connect into the GPUs, right? So the future is linear interface optics, right? Large power savings, LPO, NPO, which is near powered optics, CPO co-package, they're all linear interfaces, and LPO is by far the easiest to deploy for customers, right? So in summary, 800 gig optics with 100 gig SerDes is in volume production, 1600 gig optics with 200 gig SerDes, so 8 by 100, 8 by 200 in development. And then, LPO, we think LPO is going to be the way to kind of keep the power down. So it's all about time to market, right? The next gen of the XPO is, we can't wait for that. So